This presentation is about optoelectronic photonic emitters using wurtzite Group III Nitride semiconductors for white light generation and entangled photons. Chaudhary, Jayant Praharaj, Advanced Photonics Materials, Santa Clara and New Delhi. This slide shows a very important set of material properties for Group III Nitride semiconductors, and those are called spontaneous and piezoelectric polarization. The figure here shows the typical directions of spontaneous and piezoelectric polarization when we have one epi layer grown on top of a substrate or another underlying epi layer. I have to keep in mind that depending on the kind of epi layer and the substrate, the kind of strain can vary. For example, the strain can be compressive or tensile, and its magnitude can be different. And based on that, the magnitude and direction of piezoelectric polarization can vary. In this slide, we basically show typical bond lengths and the orbital basis for hybridization that is used to form delocalized block orbitals in these kind of semiconductors. One important thing to keep in mind is that when we do grading, composition grading in these materials, the spontaneous and piezoelectric polarization also gets graded. And according to basic electrostatic and electrodynamic equations, the divergence of the polarization leads to bulk bound charge densities, and that affects device properties. If there are abrupt interfaces between two semiconductors with these kinds of polarization, we get bound sheet charge density at the interface. Typically, a combination of electrostatic and electrodynamic equations works well for these devices. In this slide, we basically show the spectrum components for example, broad spectrum or white light generation. You have to keep in mind that the indium gallium nitride system, for example, covers the whole range from infrared to ultraviolet through the visible. And the varying the material composition can help us achieve some of the components used to get white light emission. This slide shows the effect on the carrier states, for example, electron states or hole states of polarization-induced charges and the resulting built-in electric fields. You can see that on the left, when there is no polarization-induced charge, you have the electron states that are fairly symmetric with respect to the center. But when we have polarization-induced charges as on the right, then the electron wave functions basically get shifted towards the left. And the whole wave functions behave similarly, except that they get shifted towards the right. And that has major implications for optoelectronic devices in these materials. This slide shows band profiles under device bias, and basically you can get large electron and hole concentrations in the well layers. And that can give rise to, for example, light emitting diode type emission, or even the condition for lasing or threshold population inversion can be achieved under sufficient forward bias. So to get very accurate solutions for the electron states and hole states, for example, electron states in the conduction band and hole states in the valence band, we use what is known as the 8-band K.P model, which is a fairly complex Hamiltonian, and here it's written in a basis so that it becomes matrix. That needs to be solved to get energy levels, electron dispersion, etc. Now, the polarization-induced built-in fields result in small overlap between conduction and valence band wave functions, and that reduces momentum matrix elements, and that can give rise to, for example, problems like slow modulation of lasers. One way to overcome built-in fields is using staggered well designs. The other way is to use non-polar growth axes. For example, the spontaneous and piezoelectric polarization diagrams we showed previously were for the C axis of growth or the 0001 axis. But there are other axes of growth like 1, 1, 2, power 1 axis, and even other axes which can be non-polar, but they are technologically more difficult to achieve, but they can be explored to get good optoelectronic and photonic characteristics. Recently, even one monolayer, a few monolayer quantum wells have been explored. For these, though, the K.P approximation and the effective mass approximation can become inaccurate, and we may need atomistic simulations using density functional theory or some advanced tight binding type calculations. So to understand the full device optoelectronic properties, we need to, there are two kinds of regimes. In one, we can solve the semi-classical Boltzmann transport equation using quantized block states, and that gives carrier relaxation states and other relevant parameters for the light emitting diode LED or the laser. You need to keep in mind that acoustic and optical phonon scattering and other relevant scattering mechanisms need to be taken into account. And sometimes you may need a full quantum Boltzmann equation solution, but that needs to be also augmented with multi-band effects and electron-photon coupling terms. So multiple staggered wells with different indium gallium nitride composition can lead to broad spectrum emission with good efficiency. And we can explore uncoupled multiple staggered well designs that leads to a combination of wavelengths from different parts of the spectrum. You can expect other types of quasi-continuous grading to get wide emission, but their use in quantum well or similar settings needs to be theoretically understood. And that can lead to some mixing of RGB components and broad spectrum emission. The matrix elements of momentum between valence band and conduction band states decides electron hole recombination times in LEDs and, for example, gain coefficients in lasers. Also, you have to keep in mind that strain can affect the same parameters, and so molecular beam epitaxy growth or MOCVD growth can lead to different strain relaxation, and that can lead to different device properties. These are typical epitaxial growth methods. Now, the multi-quantum well structures do have some limitations. For example, well width fluctuations can lead to coupling problems, and those need to be understood. And also, if we have many multiple quantum wells, we can get super lattice type bands. Those need theoretical understanding as well. Now, if you have quantum wires and specifically quantum dots, you can get entangled photon generation from multi-axis states. Now, these are complex many-body problems, and they also need to be solved taking into account spin angular momentum of electrons and holes. And the barrier and dot layers need to be carefully optimized to achieve entangled photon generation with wavelength division multiplexing type characteristics. This slide shows typical quantum confined states for different kinds of quantum dots, different geometries of quantum dots. So we have the conduction band electrons, we have heavy holes, light holes, and spin orbit split up holes, and they have the energy levels shown in this diagram. And this slide basically shows typical multi-exciton states due to occupation of electrons, multiple electron states in the conduction band and multiple hole states in the valence band. And those lead to entangled photon generation. In conclusion, staggered well designs and quasi-continuous grading can give some kind of white light emission. RGB light can be produced, and well dimension optimization is needed for good transport properties. And multi-exciton states can lead to entangled photons.